Hi everybody, this is a video for Monday, May 21st, and I'm hoping everybody can hear this. Sometimes the subs don't turn on the speakers, it's a very, very, very quiet sound that comes out of the projector and you really can't hear it. And then they roll the whole video that way, so I'm really hoping that everybody can hear and takes notes. So if you could take out your note-taking packet, everybody, and we're basically going to continue on. We were working on this page on Friday, the 9.3 Learning Target S. We had finished this page, but I just want to kind of go back, and if you could go to your notes pages, the extra pages in the back of your study guide, that would be great. I'm just going to do a quick review of how to think about vertical and horizontal lines. And how to graph them. So I talked about how diagonal lines get all the glory, y equals mx plus b. Students, we spend so much time thinking about that diagonal type of line that looks like this or like that, that we don't actually remember that there are other types of lines, for example, vertical or horizontal lines. So on Friday, I quickly touched on the fact that these lines have different equations. They're much more simple than y equals mx plus b. They basically just tell you what axis you're crossing through and where. So they tell you you're touching the y-axis at position 4. So if this is the y-axis and you're at position 4, you'd be here. And I said that there's no x in this equation anywhere, and that's because you never touch the x-axis. So to never touch the x-axis, we would have to make a line that is parallel to it. So there you go. That is our line, y equals 4. Never touches the x-axis, it only goes through the y-axis at 4. So, I don't know if you want to scribble all this down, if you guys just want to watch this page. If you're just watching and learning, that's fine. You don't have to write it all down on this particular page. Once I get into the packet, please do take notes. If you do want to write all this stuff down, you could have the sub pause the video at this point so you could do this. Alright, moving on to x equals -3. That is going to be a line that only touches the x-axis. Here's the x-axis, here's -3 right there. And there's no y in this equation, that means it never touches the y-axis. So in order for me to draw a line that never touches the y-axis, it would have to go parallel to it. So there you go. That right there is your line, x equals -3. Now, if it helps to make them darker, because they look kind of like an axis, some students like to make the lines darker so that they stand out so you can see what they are in relative to the actual coordinate system. Just a couple more examples before we get started with our study guide notes. And the other pages, that is. So x equals 5, here's the x-axis. It crosses the x-axis at 5, 1, 2, 3, 4, 5, which should be right there. There's no y in this equation, so it never touches the y-axis. It only touches the x-axis. So that would have to be a line that goes like this, so that it never touches the y-axis. It's over here at x equals 5. Okay, and then the last example I have for you is another horizontal line, y equals -2. Here's my y-axis. It must cross the y-axis at -2 and never touches the x-axis. There's no x in this equation. So here's the x-axis. So in order to not ever touch it, I would have to be parallel to it. So there's my line, y equals -2. Crosses the y-axis at -2 and never touches the x-axis. Now I can't zoom in and out with this camera, so I'm going to only be able to show you kind of half a page at a time, kind of like so. Again, try to pause the video if you need to take more time with this. Here's the bottom half of the page, and here's the top half of the page. Alright, I'm moving on. Okay. Okay, so now this is the page we did yesterday. We did some reflections. We drew a line at x equals 2. That's our line of reflection. In fact, we kind of made it a dashed line, not a solid line. Sorry. That was our line of reflection. And then we graphed a triangle at points A, B, C, and then we reflected that over that line like so. So here's our A, B, and C. And basically I said whatever that line is, A is exactly 1 unit away to the left, so A prime would be 1 unit away to the right. Or if C is 3 units to the right, C prime would be 3 units to the left. And see here, B is 1 unit to the right, so B prime would be 1 unit to the left. So that would be the triangle here that's a reflection. And I said that oftentimes you get this butterfly effect across the line like that. This is called the pre-image, your ABC, and this is called your image, your A prime, B prime, C prime. Alright, so what if it's not a full diagram? We're moving on to the next page. What if it's just a line segment? So for example, if we have a line, segment CD, that little bar on top means it's a line segment, and C is at -2, 2, and B is at 1, 2, or sorry, D, CD, that right there is your line segment. Now, this page is a little different because we have a different kind of line. See that line, y equals x? Y equals x is what I call a perfect diagonal line. Perfect because it goes the same distance up as it goes over. So it has a 1-to-1 ratio. So it kind of goes up 1, right 1, up 1, right 1, up 1, right 1, up 1, right 1. So it has this kind of perfect diagonal across the center of the coordinate system. Do you see that? Now again, if you want to make it a dashed line, it's not really part of our final answer graph. So in math, when it's not officially part of the space we're looking at, it's simply a line to help us see our space better. Then we make it dashed. Okay. Now how do I reflect this? What I usually do is I turn the paper so that the line is facing me, and then I do the same thing as we did yesterday. See, D is about half a square to the left of the line, so D prime would be right there. And C, this is a little harder to count, it's kind of a couple square diagonals across from the line. So I kind of go diagonal, diagonal to the left, so now I must go diagonal, diagonal to the right to find C prime. And then there you go. So there's my pre-image, there's my image, and this is what they wanted us to draw here. Graph the segment and its image. You can see the butterfly effect going on here. It's kind of got this great symmetry on both sides of the line of reflection. Alright. Now, if y equals x is a perfect diagonal line going this way, then y equals -x is a perfect diagonal line going in the negative direction. You might remember from Algebra 1 that positively sloping lines tip to the right and negatively sloping lines tip to the left. So if this line's slope is +1, this line's slope would be -1. You see that negative? You just don't see the 1 because it's not written. So this one's a perfectly diagonal line tipping to the left. And this time I will make it dashed. It's just a tool to help us make our graph. So they want us to do the same thing as we did up here. They want us to write in our original C and D points. So C, it turns out, is right on the line of reflection here. D over here. So there's my original position for my line segment CD. And now to reflect this, again, I like to do it this way. This is just my technique. I like to turn it so that the line is facing me. And then C is not going to reflect at all because C is on the line itself. So C and C prime are going to be the same position. D and D prime, not so much. I'm going to go diagonally a whole square and then another half square to get to the line if I go straight at it. So D is basically to the right of this line, half and then one full diagonal. So D prime would be a half and one full diagonal directly on the opposite side, placing it right there. So if I connect C prime and D prime, there you can see my image. There's the pre-image and there's the image. And again, you've got that kind of butterfly effect. It looks symmetrical on both sides of the line when you hold it this way. That's what you should get when you graph an image, or a pre-image and an image. Okay, so a couple practice ones here. You might want to pause the video and just try it on your own, and then roll the video and I'll show you the answers. Okay, so go ahead and pause. Try it on your own. I know you can do it. Okay, so here are the answers. Y equals x is that perfectly diagonal line they've drawn in already. And then we're going to draw in the line segment KJ, or JK, whatever you want to call it. J is at -1, -2, and K is at 1, -2. So if I turn the page again using my kind of turn the page technique so the line is facing you, there is my graph. And if I take J and I want to make J prime, it seems to me just visually it would be over here because it's half a diagonal to the right, so J prime would be half a diagonal to the left. K is like half and then a full diagonal to the right, so it's going to be half and a full diagonal to the left, placing it right about there. So if I draw in this segment of my image, there you go. Here's my line of reflection. You've got that perfect kind of symmetry on both sides, that butterfly effect going on, so I know that I did it right. Alright, and then this one, y equals -x, they want us to do the same thing with the original line segment being the same, jk. So again, j is -1, -2, and k is 1, -2. Alright, so if I reflect this across the line, y equals -x, again you can see y equals +x goes this way, y equals -x goes that way. Positively sloping line, negatively sloping line. Alright, so I'm going to turn it, and it doesn't matter which way you turn it, just so that the line is going straight up and down. And so k is about half a diagonal. It is half a diagonal to the left. K prime would be half a diagonal to the right. J is a diagonal and a half to the left from the line if you go straight at it. So J prime would be a diagonal and a half to the right. And there's your butterfly effect. You've got that symmetry on both sides, so it looks visually like I did my job. Looks good. I'll hold that up so you can see it better. There's number 3. Alright, hopefully you did them right. If not, hopefully you learned something from examples. Alright, now the next page we're going to skip for today. It does have a little bit of advanced problems. It does have answers also on the back of that page. So if you wanted to try that on your own, if you're feeling confident about this whole reflection thing, go for it. I think you guys are going to do great with this topic, so I think most of you can actually just go ahead and do it on your own, check your answers, and I wouldn't be surprised if you got them all right. Okay, but for now, let's go to the first page of rotations, 9.4. learning target S is still what we're doing. All right. In learning target S, basically, we've talked about the fact that when you move an object on a graph, that's called a transformation. And I said that there were 3 types of transformations. One is a translation. I said that was just a slide. The shape stays the same, it just slides around the graph, up, down, left, right, or whatever. And then the second type of transformation was a reflection. That's what we just finished. So it's kind of like turning a page. The reflection of my hand here would be this image here, if you just look at the outline of my hand. And there's lines of reflection across which we kind of flip those images. So we're finally on to the third type of transformation, and that is called a rotation. And most of you are familiar with the word rotation. There's kind of something that's a center of rotation, and then something spins around that. Just like a door. Doors, they're called revolving doors that just kind of keep spinning and spinning and spinning, and there's the center position on that door, which is our center of rotation. The angle of rotation just tells you how much that spinning moves. Does it keep spinning forever? Then it wouldn't really have an angle of rotation, that would be infinite. Or does it have a definite beginning and ending position? If it does have a clear beginning and ending, we can tell that angle of rotation. It might just move 90 degrees. The classroom door only moves 90 degrees. It's either shut or it's open, right? So that's a 90-degree angle of rotation for the classroom door. Some doors rotate more than that. Some doors rotate almost 180 degrees from closed. But that's what they mean by angle of rotation. Now, for this topic, we're actually going to use a little bit more kind of formulaic thinking, meaning that we're going to use letters in order to help us get the new positions of rotation. So if we have a point where the x value is A and the y value is B, and we move it 90 degrees, then the new point positions are negative BA. So basically, the x value becomes negative and turns into the y value, and the y value turns negative and becomes the x value, and then the x value simply becomes the y value. Now, if that's confusing, here's what I think about it. I just think about it as the first number, second number. So I think, oh, the second number becomes the first number, and that becomes negative, and then the first number is just now in the second number's position. So however you want to interpret these formulas is fine, and we'll show you an example of how to do that, or a few examples I should say. But if it's 180-degree rotation, basically both your x and y values change signs, so if they're originally positive, they become negative, or if they're originally negative, they become positive. That's basically what this means when you put a negative on a letter. It means to change the sign. It doesn't necessarily mean it becomes negative. And then finally, for a 270-degree rotation, that would be like a half circle plus another quarter circle. Then the y value becomes the x value, and the x value becomes the y value in opposite. So if it's positive, it becomes negative. If it's negative, it becomes positive. Now, I will say that there's actually an error on this graph. I know, believe it or not. It's not an error in the textbook, but when they've made this diagram, for some reason, the 270 degrees was marked incorrectly. This should be B negative A, like so, as I wrote it over here. So now you'll see if you kind of look around at 90, 180, and 270, they actually do match what I wrote here. Okay, so how do these work? Well, they want us, in example 2, to make 270-degree rotation. So 270 degrees is more than half a circle, but less than a full circle. It's 3/4 of a circle around. So what I usually do is I write down my original points. K is 3, 2. L, I'm just copying them from the given paragraph, is 4, 2. M is 4, negative 3. And N is 2, negative 1. Okay. Now, when we have a 270-degree rotation, AB becomes B, negative A. So, for K prime, you can see how the Y becomes the X value, so 2 is now the X value. And K prime, the original number that was the first number, in this case it was 3, changes sign. You see that little negative? So 3 becomes negative 3. And instead of the X value, it's the Y value. So again, the X value, you change the sign, and it becomes the Y value. And then the Y value simply becomes the X value. And so on down the line. So M prime is going to be negative 3, negative 4. And N prime is going to be negative 1, negative 2. So they want us to graph both of these, the original, the pre-image, KLMN, and then also the image, K prime, L prime, or I should say KLMN prime. Okay, so the original position of this quadrilateral was 3, 2, 4, 2, 4, negative 3, and 2, negative 1. Okay. The L is not prime. I just put a little dot on the page. There we go. Okay, so that's the original position. That's called the pre-image. And now we're going to make the image. So if I spin this around 270 degrees, it's going to go 1, 2, 3, and end up down here. So it should end up in this space here if I go 1, 2, 3/4 of the way around the circle for a 270-degree rotation. Here we go. So 2, negative 3 is here. 2, negative 4 is here. Negative 3, negative 4 is here. And negative 1, negative 2 is there. So as we draw this shape, it should stay the same shape. Remember, all of these transformations retain congruence, which means the shape and size of the original, the pre-image, is going to be the same shape and size of the final shape, the image. So there you go. I think I've drawn it correctly. Those two shapes do look like the same shape and size to me. Yep. So I must have done it correctly. It also looks like I've gone around 1, 2, 3/4 of a circle in this direction. So if I basically rotated that much, that's where I would get what I would get, the position, and then that would be my center of rotation, would be the center of the coordinate system. Okay, here's a few other ones we can try on the next page. Again, I'm sorry I cannot zoom in with this camera. So, here is example number 7. They just want a 90 degrees rotation. So for 90 degrees, we're going to take, I'm just copying from the previous page, you guys. This is my formula for a 90 degree rotation. Okay. So I'm copying that over here. 90 degrees, you take the original point AB, and it becomes negative BA for 90 degree rotation. And then for 180 degree notation, that would be negative A, negative B. So your AB becomes negative A, negative B. And then your 270 degree rotation would change your point from AB to B negative A. There you go. Okay. So I copied over my rules for each rotation, and really it does not say in the directions that we actually have to graph them. To me, here's the original pre-image. I like to graph my answers just to look at it to confirm that my answer is correct. The problem is that for numbers 8 and 9, the graphs would actually be off the coordinate system if we tried to graph the final image. This one would end up down here, and this one is again off the graph. So of these three, I think the only one I actually will graph the final image of will be the first one. Just that helps me to confirm that I got the right answer and that there wasn't anything weird about my numbers as I calculated them. Okay, so over here, position A, I'm just looking right here, is at negative 3, 1. Position B is at negative 3, positive 3. Position C is at 1, 3. And position D is at 1, 1. So, for a 90 degree rotation, these two numbers change, and the first number is the opposite in sign. So this would be negative 1, negative 3. This would be negative 3, negative 3. This one would be negative 3, 1, and this one would be negative 1, 1. So if I graph the new coordinate points, this is C prime, this is D prime, this is A prime, and this is B prime. If I graph the new positions, it does look like I still have a square. It's the same shape and size as the original. It's just been spun 90 degrees forward from its original position. If I'm going too fast again, please feel free to ask the substitute or whatever teacher has come to help us today, to pause the video, okay? All right. On the next example, I have the original points A, B, C, D at negative 2, 0. Again, I'm just taking these off of the graph itself. Negative 3, 2. Negative 2, 4, and negative 1, 2. So remember that little arrow in our notation indicates that something is changing, that there's an original state of it, and then it has a new position or new type of existence. So all these little arrows on the left say the original, and then after that we get the destination. Okay, so here, notice something. This is very, 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 very important. How many varies can I say? Apparently like 10. Very, 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 very important. Please pay attention, everybody, okay? Now, notice that the x and the y stay in the same relative position on the coordinate point, but it's trying to tell us here that they change sign. So, whatever A is, if you put a negative in front of it, it would change the sign. So if it was already negative and you put another negative in front of it, it would change to a positive, because two negatives cancel each other out and become positive. So basically what this is actually saying when you use a formula where you put a negative in front of a letter is that you want that letter to change sign. So both x and y are going to change sign. So for example, B prime is going to be 3, negative 2. Do you see that? How they both are the same quantity, except the fact that you have opposite signs. That's what this means. That's what it means when you put a negative on something. It wants that number, just the opposite sign. So C prime would be 2, negative 4. And D prime would be 1, negative 2. You see that? Changing all the signs. Now 0 doesn't have an opposite sign. 0 is neither positive nor negative, so when we try to change 0 into something that's opposite sign, we can't do it, we just put a 0. But the 2 we can change from negative to positive. So this is an example where I really want you to understand how formulas work, where again, if there's a negative that's placed in front of a letter, that just simply means to change the sign of that number from negative to positive or positive to negative. Now again, if I try to draw this, it would be down here off the graph, but they didn't ask us to make the final sketch of the image. They just wanted us to create the list of coordinates for the image, and we did that. So technically this column right here is our final answer, or here. So if you want to put a box around it, this is A prime, B prime, C prime, and D prime. This right here is our answer the way that they've asked the question. List the coordinates of the vertices of the image. There you go. Alright, and then finally, AB becomes B, negative A, or in this case, opposite A, right? So over here we have A at 0, 2, B at 1, 4, C at 6, 4, and D at 5, 2. So, okay, what's going on here? So it looks like the Y value becomes the X value. So I'll start with that. So the Y value becomes the X value on each one of these. And then the X value becomes the Y value, but it changes sign. So all of these would be, except for 0, the opposite sign, like so. So again, if I graph this, it would kind of be down here, and it would go off the side of the graph that they've provided for me. So that's okay. They just want us to write the coordinates, and there they would be. Okay, and then this is the last thing we're going to do today, bottom of this page, examples 10, 11, and 12. Really, again, they just want you to remember that when a shape rotates, when it slides around with a translation, when it's reflected across a line of reflection, all these types of transformations, the shape stays the same shape and size. There's a congruence between the original shape and its destination. So, I can tell you right now that this section right here, X, is going to be the same as this one right here, because these two shapes are congruent, and so that longer base on this trapezoid here will match the length of this one over here after it's been rotated. So I know that X is 11. I also know that Y, this section right here, will be the same length as X minus 4. That section right here. Those two lengths will be the same. So if Y is equal to X minus 4, I can find the answer for Y because I know what X is. X is 11. So if I do a substitution from my original answer of X equals 11 into this equation for where I know Y equals X minus 4, I should be able to calculate very simply by taking 11 minus 4 that Y must be 7. And so that's really all you have to do. You have to just find matching parts. So X matches with 6, and Y matches with 2X plus 3. And since I know that X is 6, I can do a simple substitution whereby I would then multiply first and then add to find my Y value of 15. So if X equals 6, lining up things that are the same, I can create another equation where y equals 2x plus 3, and then substitute the x value here, and find y to be 15. So if you want to pause the video now and try number 12 by yourself, they're all whole number answers. Go ahead and pause now. Give it a try. And then when you run the video again, I'll give you the answers. Okay, so here are the answers to number 12. I know that this line segment from here to here must be the same as the line segment from here to here. So I know that 4s is the same as 24. Now this one I'd have to I'd have to divide on both sides by 4 in order to find the value of s to be 6. But then I also know that r is the same length, this little segment right here, the shorter base on the trapezoid, is the same length as this one up here. Again, the shape is the same, shape and size. They are congruent no matter if it's rotated, slid around, or reflected. So I know that that little section here is the same as that little section here. So I know that r is the same as 2s minus 3. Now I can find the value of r because s is 6. So r equals 2 times 6 minus 3. That's 12 minus 3. So r equals 9. Alright, that's the end of my video, you guys. I hope to be back tomorrow. Have a good Monday, and I'll see you then.